logarithmic and exponential equations. It's going to be a little bit of both in this section. The key thing to remember is that if it's a log equation, like the original problem has logarithms in it, you need to check your solutions. Because the domain of a logarithm is restricted, we've got to check those solutions to make sure that we're not getting a negative or a zero inside of a logarithm out of that. So there's a possibility of extraneous solutions when we're solving these log equations. So let's just start with those. That's the best ones to start with because they're the most restrictive. So let's take 2 log base 5 of x is equal to log base 5 of 9. Okay, so anytime we have a logarithmic equation, the first thing that you want to do is try to condense any log properties that you have on one side that has, if one of the sides has some log properties that could be condensed. So on that left side, we've got a power property right there. So that could be condensed into log base 5 of x squared. And the reason you want to do that is so that you can then get rid of the logarithms. Okay, so when you have log base 5 of x squared is equal to log base 5 of 9, what's going to happen is the logs are going to go away, and you're going to get x squared equals 9. The math that makes that happen is the inverse of a logarithm is an exponential. Okay, so we're going to exponentiate. That's the term for the math that we're doing with a base of a 5. So we're going to make 5 the base. What that does is it uses one of the log properties, and it's legal because I'm doing that to both sides. I'm making 5 the base, and then this 5 raised to the log base 5 of x squared, the base 5 and the log base 5 are going to cancel each other out. That's the math that makes that happen. So that cancels out. It also cancels on the other side. So we end up with x squared is equal to 9. Just like I just did there. 5, and then this little caret symbol means this becomes the exponent. That's what that means. So 5 is the base. This little symbol means make this part the exponent. That's what that means. Okay. And then now we have x squared equals 9. We got rid of the logarithms, so we can then take that and solve that like a normal math problem. So how would we solve that? Yeah, take the square root. And if I bring the square root to the table, what else do I have to put in there? Plus or minus. Yeah, that's the key. That gets us x equals positive and negative 3. So we got two answers. We got x equals positive 3. We got x equals negative 3. We need to check those in the original problem to make sure we don't have a logarithm with a 0 or a negative in it. We can have logarithms of positive numbers, but not zeros or negatives. So if I go back up to the original, if I plug in the positive 3, log base 5 of positive 3 is good. That's the only place we got to check. If I plug in the negative 3 plugged in there, that's a log of a negative. That can't happen. So that is an extraneous solution. So this is an extraneous solution. It means it's a solution that we found through the algebra to solve it, but it doesn't check in the original problem. It doesn't work out of that. So key thing, it's extra. Extraneous, the root word there is extra. So it's an answer you found, but it doesn't check in the original. Okay? That's what an extraneous solution is. It's an answer you find that doesn't check in there. It is possible for when you find more than one answer for both of them to be good and you keep both of them. It's possible that one of them is bad and you throw it out. Technically, it's possible that both of them are bad and you throw both of them out. That's not likely. That's the least likely thing to happen. But it's possible that you keep both of them. So you've got to just check them all. Anytime you have a logarithm in the original problem. That's what we've got to do. We got to check. All right, so let's take another problem. Let's say we had log base 5. I'm using the same base here so that it kind of extends our idea here. I'm going to set that equal to 1. So I have log base 5 of x plus 6 plus log base 5 of x plus 2, and that's all equal to 1. So we have logarithms on one side of the equation this time, not two sides. Okay. So again, anytime you have logarithms in the problem, you want to see if you can condense any of those logarithms. So on the left-hand side, can I condense that? Yeah, I can make it a single logarithm. We want to make it a single logarithm on that side. So what is the math that's going to go on between that x plus 6 and that x plus 2? Multiplication. So that's going to be log base 5, x plus 6 times x plus 2. And it's still equal to 1. So I'm going to go ahead and multiply those two together and get x squared plus 8x plus 12. Anytime I'm condensing there, I want to go ahead and put them together. And then, so x times x is the x squared, 2x, and 6x, that's the 8x. 6 times 2 is the 12. Now, here's where we get rid of the logarithm. Okay? The base of the log is a 5, just like it was on the first example. So to get rid of the log base 5, I'm going to exponentiate with the base that we have there. So I'm going to exponentiate with the base 5. On the left-hand side, that 5 raised to the log base 5 stuff, that is one of our simplifying properties, and that cancels out the logarithm. So we end up with x squared plus 8x plus 12. And on the right-hand side, instead of having a log to cancel out, we've got a number. We got 5 raised to the first power, which is how much? No. 5 raised to the first power. It's just 5, yeah. 5 raised to the 1. It's 5. Now we have a quadratic equation. So we got to go back to chapter 4 stuff. How do we solve a quadratic? What do we need to do? Yeah, make it equal to 0. Move the 5 over. So move that 5 by subtraction. So we end up with x squared plus 8x plus 7 equals 0. And then we've got our options as far as how to solve that quadratic. Factoring is the best option if it will. If it won't factor, then quadratic formula is the way to go. So I'm going to go factoring. What multiplies to be 7 and adds to be 8? Yeah, really easy. 7 and 1. So that's x plus 7, x plus 1. Set those factors equal to 0. Get x equals negative 7, x equals negative 1. So we got both of them to be negative numbers there. I got to go back, because my original problem had logarithms in it, I need to go back to the original problem and check those in that log base 5 of x plus 6 plus log base 5 of x plus 2. So when I plug the negative 7 in, if I put a negative 7 in for x, that's going to be negative 7 plus 6, which is how much? Negative 1. So I don't have to go any further. That screwed it up right there. So negative 7 is an extraneous solution because I got one of the logarithms to be negative out of that. So that's an extraneous solution. Let's check negative 1. Plugging that one in. Sorry. Negative 1 plus 6, that's positive 5. That's okay. What's negative 1 plus 2? Positive 1. That's okay. We didn't have a 0 or a negative in the logarithm. So the negative 1 is a good answer. It's a keeper. So we checked it. It worked. Okay. So the x equals negative 7 is extraneous. So I like showing it that way. That way you can see the answer and not have to panic about it. All right. Now, let's try example C. Let's say we had natural log of x plus natural log x plus 4 equals natural log of x plus 10. Yeah, x plus 10 is good. So here we have natural logs in there. But here's this one is similar to the first example, but also similar to the second example. We got different base on our log though, so a little bit different on that part. So on the left hand side, I got 2 logarithms. On the right hand side, I got 1 logarithm. So I want to condense the side that has more than 1. So how do I condense that left side? Multiplication. Addition turns into multiplication, so that's going to be natural log. And I'm just going to go ahead and distribute that and get x times x is x squared. 4 times x is 4x. So just went ahead and did the distributive property there. Now, what do I exponentiate? Now that I got a single logarithm on the left and a single logarithm on the right, what exponentiates to get rid of a natural log? E. Whatever the base of the log is, that's what I'm gonna exponentiate with. So that's going to cancel out the natural logs on both sides. So it's nice when there's logarithms on both sides. It makes it a little easier. So here we have x squared plus 4x is now equal to x plus 10. And then, what do we do next? Because we're trying to get it equal to what? 0. Anytime we got x squared or x cubed or something like that, we want to get it equal to 0. So we're going to subtract x, subtract 10. That's going to cancel out everything over there. There's my equals 0. And I've got x squared plus 3x minus 10 equal to 0. We've got a nice quadratic there. I hope it factors. I'm not sure. It does? Yeah. What multiplies to be negative 10 and adds to V3? 5 and negative 2. That's great. So I've got x plus 5, x minus 2 are my factors. What are my solutions here? And positive 2. Okay, so x equals negative 5, x equals positive 2. Now we want to go check those in the original. Remember, doesn't really matter what the base of the log is. We can have a 0 or a negative inside of the log. So if I plug in the negative 5, it screws up on the very first one. Also screws up on the second one. Works in the third one, but if it messes up in any one of them, it's an extraneous solution. So this is extraneous. What about positive 2? Does it work? Yes, we're good. We'll keep it. Okay. So logarithms condense. Get it to single log on each side or one side, or whatever. You'll condense your logarithms. Then you're going to exponentiate with whatever the base of the log is. Okay? Exponentiate with whatever the base of the logarithm is. All right. Now, let's get into a few exponential equations before we get out of here today. So this is exponential because it doesn't have a logarithm in it. And the variable is in the exponent. So exponential equations, we did some of these back earlier in maybe it was section 6.3, I think, or 6.4. I can't remember which one. But when we were doing those were like level 1 stuff where we could manipulate it to get the base the same. The difference in these is the fact that, okay, this is 2 as a base. I can't rewrite 5 as like 2 to the second power, 2 to the third power. It isn't a nice number out of that. So we've got to use some logarithms to solve this. So the nice way of solving that would be if you've got a single exponential on the left side and the right-hand side's a regular number, use the log that has the same base as the exponential. So if I take the log base 2 of 2 to the x, and then I do the same thing on the other side, that's going to, right there, that left side is the property of logarithms where that 2 and the log base 2 cancel each other out, and we get x equals log base 2 of 5. Log base 2 of 5 is a number. We're going to get a decimal approximation. We got the exact solution. This is my exact answer. I want the decimal approximation for that as well. We're going to go 3 decimal places out of that. So on my calculator, I'm going to do log base 2 of 5. So I can do alpha window, go down there to log base 2 of 5. Or if I've got the TI-83, I can do log of 5, close the parentheses, divided by log of 2. That's the same decimal. So we're going to round that to 3 decimal places. So this would be 2.32. What is the 1? Does it stay or go up? It goes up. So 0.322. 2.322. That one wasn't too bad. Pretty nice. Let's try this one. 4 to the x plus 3 equals 9. So here we have the left side's a base 4. The right side's a 9. 9 is 3 squared, not 2 squared or 2 to the third. Or if it was an 8, it'd be 2 to the third, and we can change that to 2 squared and work with it. But because it's a base 4 and a 9, you can't manipulate those to be the same base. So what logarithm am I going to use to get rid of the exponential? Log base 4. So I'm taking the log base 4 of both sides. So on the left-hand side, the log base 4 and the base 4 from my exponential cancel each other out. So we end up with x plus 3 equals log base 4 of 9. Okay. Now, not quite as easy as this one because we got a little bit more work to do to get x by itself. What do I need to do to get x by itself? Yeah, just subtract 3. And that's going to give us x equals, and then log base 4 of 9, that's a number, and then minus 3. So there's our exact solution. We want to, again, get a decimal approximation for that. Okay, so let me get my log base action happening here. And so we can see that whole decimal there. So log base 4 of 9, and then minus 3 on the outside. Negative 1 point, and then the 0 we can stay the same. So negative 1.415, as Sarah said there. Notice that I'm not going back and checking these. Why am I not having to go back and check these? That's right. Exponential, if you remember when we did exponential functions earlier in the chapter, their domain isn't restricted. It's all real numbers. So as long as we're getting a real number solution, then we don't have to check that in that. It works. As long as we're doing our math the right way. Okay. We got time for one more. And then we'll have to finish up tomorrow, but that's not a big deal. Let's do 8 times 3 to the x minus 6 equals 5. All right, so here we have a little bit more on one side than just an exponential. We have 8 times an exponential is equal to a number. So like we were doing with the logarithms, we want to isolate that logarithm to get rid of it. Here we want to isolate the exponential. So the first thing that I want to do is get rid of that 8 that's hanging in the front. So how do I get rid of that? Yeah, just divide by that 8 because that's the inverse of multiplication. So that's going to cancel that out and give me 3 to the x minus 6 is equal to 5/8. Now this looks similar to the others. You just got a fraction over there, but it's still a number. So what do I do to get rid of the exponential? Yeah, take the log base 3 of each side. That's going to cancel out our logarithm and our exponential there and just give us x minus 6 equals whatever log base 3 of 5/8 is. All right, finish that problem up for the tomorrow, and we'll do a fun one after that tomorrow to finish up.